All right, today's lesson we will learn how a catalyst can speed up a reaction. This is the fourth and final method of speeding up a reaction. Uh, I would put this almost as complicated, the most complicated, but it sort of sits roughly on par with temperature in my opinion. Let's talk about what we talked about this morning. This morning we talked about concentration. We said that concentration is the amount of reactant or amount of stuff in a solution. So if you've got a lot of reactant, then you're going to have a lot of reaction going on here. Where if you've got very little, if it's very dilute and there's not much going on, then you can see these things can fly around, but they don't bump into each other. They don't even meet. So therefore, the higher the concentration means the more reactants. The more reactants means more collisions. And the more collisions mean the more product, or the faster the product is made. We also saw a second problem, which is if you don't have much reactant, you're not going to get much product anyway. So yeah, that's why you've got to be careful about concentration. There is a cheap way to get around this concentration problem, is to instead compress it. If you compress the liquid, which you can't really compress a liquid, but you can evaporate the water away, or if you're, if you've got a reaction happening in a gas cylinder, you can compress that gas cylinder. And then once that's in a smaller reaction, you're more likely to get a smaller vessel, you're more likely to get a reaction then. And that can speed up the reaction too. So that's two ways that we can go about doing it. The next way that I wanted to talk to you guys about is the catalyst. Now, I wasted a fair bit of my lunch working on these slides. I wasted my whole lunch working on these slides because I wanted the slides to look really good for you guys. And you might think, oh my God, sir, you love us so much. I do really want you guys to have a good lesson, but I'm also doing it for my own benefit. If I make these slides look really, really good, then that means that next year I've got the same really, really good slides. But yeah, I don't want to just teach this by I don't want to teach this by just slabs of text. For me, what's really, really important is to show you guys some images and some, in my cases, bad animations. So get ready for some bad animations. We're going to talk about a catalyst. Now, there's a little bit of text in this lesson, so I apologize for that. I've tried to cut it down to as few words as possible, but yeah, this is the bulk though. So this is the bulk. There are two slides with lots of text, but I think this is the biggest one. So yeah, let's get this done today. So a catalyst increases the rate of reaction, not by increasing the amount of collisions. Now this is interesting. If you think of temperature, that increases the amount of collisions because they're moving faster. If you think of surface area, you're adding more reactant in more places to react, so you're increasing the amount of collisions. Concentration, you're putting in more stuff, so you're increasing the amount of the possibility of a collision. But catalysts don't do it like that. Catalysts increase the reaction rate the opposite way. Instead, it forces the reactants to interact in the correct orientation for a reaction. So instead of making more collisions, it's making each collision count. It's like instead of throwing 100 balls in the air and hoping one of them goes into the basketball hoop, it's instead throwing a basketball but being very careful that you know which way you're throwing it, lining up your shot, standing, I don't know, I don't play basketball here, people, so help me out here. Standing, with your weight properly positioned. So that's why, that's the difference. It's a different way of making sure that you get a basketball in the hoop, is making sure you do it properly. This is done by locking the reactant into place on a large molecule known as a catalyst. So let's see how it does this. So this big ugly thing here, I would like you to draw something like this. And this is going to be our catalyst. And you can see here that you've got this sort of this hole here. And that hole is going to be important. And you've also got these divots, and these divots are going to be important as well. So let's see how it works. We're going to bring in this molecule here. This molecule is going to float around and it's going to get stuck. And it's going to get stuck in this divot here and this divot here. This molecule, by the way, is actually modeled of carbon monoxide. So carbon monoxide could come in and get stuck. And you might, if you want to, it gets stuck because it's going to be attracted to certain parts of the large molecule and it won't be able to leave. Then what we're going to do is we're going to bring in another molecule. And this molecule here actually represents oxygen. So that oxygen is going to float around, it's going to get stuck in this crevice here. And then what happens is that because they're stuck and they're close to each other, this can now react. And the other one as well is it has to depend on the orientation. This is really good for the reaction because this oxygen has to react with the carbon dioxide, with the carbon. This oxygen needs to react with this carbon in order to make it work, not with the other oxygen. So then what happens is that you can create a reaction being made and you make a product. In this case, you would get carbon dioxide, CO2. Now, again, so let's go through it again. So you've got first one reactant comes in and gets stuck. The other reactant can come in, it can also get stuck, and then they react. Now, some points that I want to make about this type of reaction is it's a lot easier for the chemicals to react because they are being locked in place, and it's like kind of being like, here, you are attracted to you, force you together, and then we've got a reaction. It's yeah, once those, I don't know what else I was going to say. Once those two things react, it can then, shit. Just give me a sec, sorry, I've got to fix something. I forgot that I did this. There we go, fixed. Okay, back to here. So here we go. Here comes the carbon dioxide, flies in, gets stuck. Next one, here comes the oxygen, flies in, gets stuck. Those two lock together, and then it can then leave that, and then leave the catalyst. I will point out, and this is what I remember what I was going to say. I will point out the carbon monoxide and oxygen will react to make carbon dioxide. That's not balanced, is it? I've got three oxygens on the left, 2 oxygens on the right. I need to change this. I need to increase the amount of oxygens here. Now I've got 4 on the right, 3 on the left. There we go. 2. Balanced. Now, this will occur, this reaction on the top will occur without a catalyst. That's my point. You could make carbon monoxide will react with oxygen to make carbon dioxide, but the rate that it makes carbon dioxide is going to be really, really slow. So slow, in fact, that it might not ever really occur. So that's why catalysts are really useful. They can make reactions that might never occur actually happen. And they actually happen quickly. So that's how a catalyst speeds up a reaction. It forces the reactants into the right orientation. So it's sort of like, it's like doing a reaction step by step. Also in that previous thing, I saw the oxygen coming in, for the carbon monoxide coming in first. It actually doesn't matter what order they come in because they'll be locked anyway. And there is also millions upon billions of these carbon atoms. So eventually, one of them is going to get stuck. Now, I'm going to change the slide unless someone says, no, wait, sir, please. Okay, change the slide now. So this is the basics of the catalyst. If you take nothing away from today, you take this away, perfect. Sometimes this is referred to as the lock and key method, because what happens is only carbon monoxide molecules can fit in there, and only oxygen molecules can fit in there. And that's why you get this reaction, because only certain molecules can fit in those spaces. You could add a catalyst to something which has got a bunch of different chemicals in it, but only those molecules would react. Catalysts only work with specific molecules. So you can't just use any old catalyst. So now, I want to quickly talk to you guys about catalytic converters. Now, a catalytic converters are a large device in your car just before the exhaust pipe. Now, this is the reason that I showed you carbon monoxide turning into carbon dioxide. This is exactly what a catalytic converter does. When you burn gas or petrol in your car, you will produce a lot of hazardous chemicals. These include carbon monoxide, which is incredibly poisonous, nitrous oxides. Those nitrous oxides are pretty bad for the environment. They cause a lot of depletion of the ozone, plus they're really toxic, plus they're what makes they're what are the dark sort of things they're brown. So it's when you get lots and lots of carbon and nitrous oxides in the atmosphere, you end up with a bit of a smoky haze. And the last one that we've got here is then we've also got HC, so just general hydrocarbons. Once these go through the catalyst, right, they do a bunch of reacting, and then they come out as H2O, carbon dioxide, and nitrogen, which is, all three of these are a lot safer. Don't get me wrong, carbon dioxide is not great, it's a greenhouse gas, but you know, these other two, you know, nitrogen is definitely safe, 70% of the world of its nitrogen, and water is pretty safe too. Bonus marks. Can anyone in chat tell me after you copy this down, why do you think that the catalyst is a honeycomb structure? Who wants to give a guess? Why do you think that it's important that we use a honeycomb structure? Why don't we just put a massive rod of catalyst in there and get it to deal with it? We've got some guesses coming in. More surface area, cuz. You are right, Talik. Honeycomb structure is going to ramp up that surface area. So then it doesn't matter where it hits. It's because it's got such a, it does matter where it hits. Because it's got a honeycomb surface, it means there's a really high chance that it's going to smack into something, because there's like so many different layers of there's so many different layers of this surface, in fact, that's going to react with something as it goes through. So that's why we use a honeycomb structure. It's very, very, very small, so it's very, very, you know, but yeah. So it's got different catalysts on there. So it's actually not just one catalyst, it's got different types of catalysts, but they're all put on this ceramic structure. But yeah, if you're interested in cars, yeah, this is pretty important. It's also important to know that I don't think I think it's like you shouldn't have to replace your catalytic converter unless if you're getting a lot of black smoke coming from your car. One of them could be the fact that your catalytic converter might be stuffed and might need to get replaced, but then it's probably also because you're not your pistons aren't burning the fuel properly, so you're ending up with a lot of stuff. So, you know, I'm not sure if you can replace it, but yeah, anyway. So that's a catalytic converter. The next slide has got the next hardest thing to explain on there. And so, yeah, I'm going to throw this up here. This is the energy curve, or actually, I think it's properly called an energy profile, but you know, whatever. What I want you guys to do first, I'd like you to draw this image down here before I start to explain it and label it. I'm not sure if you've seen an image like this before, but yeah. And then I'd like you to write down this here, because yeah, there is a little thing in light gray. I don't want you to write that down, obviously. That's just, you know, a heads up. Yeah. I'm going to give you guys a minute to copy this down first before I start to talk about it. You guys ever seen those things that you can attach to your exhaust pipe and that makes it like really, really big so that it, yeah, so that the car sounds like it's a bigger car? They put it on like sports cars, I think, to make it sound like, oh, a bigger deal, when it, you know, all you're doing is just, you know, making the exhaust pipe bigger. I don't know. I'm not a car guy. Yeah, there's a lot of chemistry and physics and stuff with cars, so I do appreciate them. I sort of get them, but yeah. I was saying to my wife last night, we were talking about just stuff, and I'm sort of of the opinion like cars are so, like, automobiles are just, and engines in general are just so amazing. The fact that we've, like, if you think about it, when a car in a piston, that's an explosion. We have gotten so good at harnessing an explosion that we use them to drive around. And it's like, when you start thinking about it, it's like, yeah. It's like, if you think about an explosion, you know, you're like, oh my God, it's so chaotic. It's like things are going everywhere. But then you think about a car, it's like there's millions upon billions of explosions happening on that thing on the way from your house to the corner shop. And it's like, you know, we've harnessed them so well that, you know, you barely even notice it. Anyway, enough rambling. Let's get to the point here. We've got about 10 minutes before I run out of time. And it's weekend, thank God. Let's finish it up then. A reaction can be thought of as an energy curve. So I want you to add these labels to it. Reactants lose or gain energy and become products. By the way, for those of you guys that are a little bit nerdy and you guys remember last year, this is the difference between endothermic and exothermic. This is not on the test, but just heads up. Exothermic is where you lose energy, whereas endothermic is when you gain energy. So this here would be an exothermic reaction because you are losing energy. But in order to make these products, you need to break the chemical bonds. And this requires an activation energy. This here is the activation energy. It's the amount of energy you need to put in before the reaction will even go ahead. Sometimes you need to put a lot of energy in, and sometimes you don't need to put much at all. Some reactions pretty much just happen even without you doing anything. Like there are some reactions you just need to shine a little bit of light on and they'll start reacting. There's some reactions that will react to sound. If you put a lot of sound, the chemical reactions start happening. So yeah, the activation is how much energy you put in. But what if I was to tell you Well, what do catalysts do? Catalysts change this. What a catalyst does, and I've just added this last line to the bottom. What a catalyst does, and I'd like you to add this to your picture. I should have labeled it, but that's all right. What a catalyst does is it makes it easier for the reaction to occur. And because it's easier for the reaction to occur, and why is it easier? Because it's locking those chemicals in place. Because it's easier for that chemical reaction to occur, it actually requires a lower activation energy. You actually don't need to put as much energy in order to get a reaction to occur. And that's a different way of explaining how a catalyst actually speeds up a reaction. Ultimately, all the catalyst does is it holds molecules in place and allows a reaction to happen. But you can think about it as instead as lowering the activation energy. No other way of speeding up reactions do this. Even temperature doesn't do this. Temperature just means it's more likely to have the right activation energy. It doesn't lower the activation energy. Okay, I'm going to give you guys another 25 seconds to jot down this in the picture. If there are any questions on what's going on, let me know. The new activation energy is this high. So if you look at that, that's a lot smaller. But the energy of the reactant and the energy of the products are the same. You're not changing the reaction, you're just changing the reaction, you're just changing the size of things. Okay, one important thing, I'm just freaking out because I feel like I may have forgotten to add this, but I do. Can I get you to just add one extra line? I know it's not written here, but it was supposed to be on a previous slide. And this is actually one really important thing, and that's this. Catalysts are not used up in the reaction. So I just want you to add that last line somewhere, wherever you're writing it down, to your idea. I will put this on the slides afterwards. But yeah, catalysts don't get used up. So that means that you can actually use the same catalyst over and over and over and over and over again, which is pretty good because some catalysts are made of like really expensive metal. This is why you don't need to replace your catalytic converter every 5 years in your car, because ultimately the catalyst doesn't get used up. So therefore, it should be just as good as when you started. So that's why when we talk about catalysts, they're really good. Not only do they lower the reaction rate, but they don't get used up. So you can keep reusing them. You actually don't need much catalyst at all, because instead of getting used up, you can just use it again. So that's just one. Catalysts are really good. If you can get a catalyst for your chemical reaction, then you're in a good place. Now I'm going to keep going. I've got 5 minutes left, but when we get to the end of the lesson, I'm just going to call it there, and we can cover the rest of it later on. But I'm going to talk a little bit more because the last part is enzymes. Now you guys have learned about enzymes already, so this shouldn't be news to you. You guys should have learned this in year 9 if you had a good science teacher, which I assume you did, because all the science teachers are good. But yeah, let's talk about enzymes. Because enzymes are biological catalysts. Okay, an enzyme does exactly the same job as a catalyst would in a car. The only difference is that they are found in living things, including us. So including in our digestive system, which is where you guys should have seen it from last year, and even in our blood. So I just want you to jot this part here down. And then I think the last little bit of the lesson is just going to be me showing you guys some pictures. I'm not going to get you guys to write anything more down. I'm going to show you some pictures, and I might get you guys to jot some things down next Friday when I see you next. But yeah, just get that bit there jotted down, and then I'm going to show you some pictures. I will open up the enzyme one to style, just in case you've got some students, some of you guys are super fast working through it. But again, as I said, all of next week is pretty much going to be a catch-up week. There's not going to be any new content, because essentially what I've done is I've filled you guys up with a lot of content this week. So enzymes are biological catalysts. They are found in living things, including our digestive system and our blood. For example, in our blood, we have an enzyme which is known as hemoglobin. This is an enzyme or a catalyst. It's known as hemoglobin, and hemoglobin, what hemoglobin does is it catalyzes the reaction. No pencil here, don't have to copy it down. It catalyzes the reaction of adding cell plus oxygen goes to cell, whatever, whatever. And that's what its job is. Its job is an enzyme that does this. And it doesn't look like it's got any, it doesn't look like our picture like before of the active site and stuff like that. But that's what this area in the middle is sort of for. It's for things to fall in and get stuck and attach and then react. So that's how hemoglobin works. It's actually a very, very, very complicated structure. It's got an iron molecule, an iron atom in the middle, and then the rest of it is just this big, complicated structure. Luckily, you guys don't need to know about the complicated structure. You just need to know about the theory, which is molecules get locked into certain places and then they can react. And that, because they're locked in, because they're locked into certain places, that means that it lowers the activation energy. And, you know, the other beautiful thing is the catalyst does not get used up. Here's another picture, same picture. This is an enzyme. This is what we refer to as the active site. Here comes in this case, it's substrate, which is what we would call reactive. In this case, it's a lipid. Lipid comes in, binds to it, it reacts and gets broken up into smaller parts. And those are the products, the fatty acids are the products. I'm not going to get you to copy this down. There's only 4 minutes left. We'll do that on Friday next week. But here are some reactions. Amylase, protease, and lipase, these are all enzymes, which means these are all catalysts. And each of these guys reacts to form these products. This is what you should have learned. Yay! Someone said, I remember these. Perfect. That's exactly because this is what you learned last year. I'm not going to get you guys to jot these down because personally, that's not what we're studying this year. But it's meant to be oh yeah, these are enzymes. What they do is that they make these chemical reactions go faster. But if you look as well, notice how these don't get used up. They're on the left and they're on the right of the reaction. They don't actually get destroyed. You can use them over and over and over again. They will wear out over time though. They will get like destroyed by random things, but you can make more of them. And that was it for the lesson. So I might get you to copy this down next week, but that was it for catalysts. So catalysts are pretty cool. So what we've done now is we've covered, let me go back all the way back to here. Where is it? We've covered each of these 4 ways of increasing the rate of reaction. These are the 4 ways that I told you about at this time last week. And over this week, we have covered each of these 4. What we're going to be doing next week is practicing, understanding each of these 4. I should be able to say, hey, I've got a really concentrated solution of vinegar and a really dilute solution of vinegar. Which one's going to make the reaction go faster? You know, oh, that's a concentration one. It's like, oh, I've got this new catalyst. What's that going to do to the reaction? I want you to get really confident. So that's what we're going to be working on next week. We're going to be tying these things together. And then pretty much we're done. So I think that after next week, we may even start talking about, you know, moving on to doing a test. But I'm not sure yet. I'm going to have to contact all the other science teachers to find out what the plan is. But yeah, that was it. That's this lesson. That's now 3:06. I'm going to stop